Thank you. I will begin with a word of prayer. Heavenly Father, we thank you for this day. Again, Lord, I thank you for these students, for this week. Just pray that you'd help us to glorify you in what we do this day, Lord. In your name I pray. Amen. So I'll get started here. This is what I've written. Is that was you?
Oh, yeah.
How dare you? Wait a minute. Interesting. Daniel, cease and desist. I made you the cameraman. I can unmake you the cameraman. It's here. This is the last visit of a child of mine this semester. But anyway, this is the fundamental theorem of cyclic groups, according to Nicholson. And I thought it would be good to state it, prove it, and give an example that illustrates some of the theorems we've had in this section, and then I'll go on to isomorphism. So I'll get to it here. We already have, so if H is a subgroup of G, let's prove one, right? If H is a subgroup of G, then there exists M in a, the integers, such that what? H is equal to the cyclic, it's a cyclic group, right? It's generated by G to the M for some M. This is a previous theorem. We proved every subgroup of a cyclic group is cyclic. So such an M exists. And then let D equal the greatest common divisor of M and N, right? We're trying to do, we want to show now what? We want to show that H is generated by G to the D, and that D is a divisor. Well, the fact that D is a divisor of N, if D is the greatest common divisor of M and N, we definitely have that, right? So what do we have to show? We need to show that, in fact, H is generated by G to the D, and that will prove one. Okay, so what does this mean? There exists what? Say X and Y in Z such that what? D is equal to MX plus NY, right? So G to the power D is equal to G to the power MX plus NY, right? Laws of exponents say that this is what? G to the M to the X, right? G to the N to the Y, but what's G to the N? G to the N is what? Is 1, right? Yeah. So this is just GM to the X. What's that say? G to the D is an element of what? The cyclic subgroup generated by M, aka what? H, right? But that implies that the cyclic subgroup generated by G to the power D is a subset of H. We're assuming G is a cyclic group with generator G. That's still true. I didn't write it in the proof. Sorry about that. Now, what else do we need to show?
Other direction.
Right. So, let's see here. What if we take an element of H? What would it look like? Let's, I need some other, I guess I haven't used alpha. If alpha is an element of H, then what? Alpha equals to what? Yeah, G to the M to the, let's say, X prime for some X prime. what would I like to do? I'd like to rewrite that as what?
We know that D divides M, so we want to rewrite it as G to the D is something. The fact that D divides M.
Right. I think I'm making this too complicated here. Scratch. Hey, that's stupid. Let's try that again. Let's see here. So, D is the GCD of M and N. What's that mean? Yeah, D divides M. Thank you. Which means what? M equals to? DZ? Sure, why not? So if M so then what? So G to the M is G to the D dz, or G to the D to the Z. What's that say? Right, that says that GM is an element of the cyclic subgroup generated by GD. But this generates an arbitrary element of H, right? So this implies that H is a subset of the cyclic subgroup generated by GD. And so if you look at it, we have this right here, right, and this right here. So there you go.
When you have G in bars up there, should that be capital G, like the cardinality of set G, or are you talking about something else?
Well, this is notation that is used in Nicholson and we will use on occasion, which is if we have an element and there's no absolute value, then it's understood that if we write bars around an element, it's the order of the element. It's another notation for little o. I don't know if you've noticed or not, but the little o notation gets really kind of distasteful when applied to permutations, especially like his example with order and sigma. No, that's not good notation. Like, I don't know, you look at it and I just see, oh. It's like, what? I mean, so we don't have to be a slave to notation. Sometimes this is a better notation. Sometimes that's a better notation, right? Just like with Zn, I'm not going to be dogmatic about we have to use bars, we don't have to use bars, right? There are places where using bars is clarifying. There are places where it's just a nuisance, right? Okay, how about number 2? If K divides N, then N is equal to KD for some D, right? So if I look at, I'm sorry, phew. All right, I'm sorry, I should just move on to isomorphism. I mean, what's wrong with me here? So let K be a subgroup of G. Suppose K is a divisor of N, all right? And big K is a subgroup of G. I feel like no one here is taking notes in Crayola markers. seemed like the writing instrument of a child. Huh. Let's see here. Where was I? Oh, yeah. Okay. So we have a subgroup of order k, right? By part 1. See, not letting him be in Little League is paying off right now. Part 1. We have that the subgroup is generated by g to the d, where what? D is the divisor of n, right? That was part 1, which I have proved in a annoyingly slow fashion. And then, what do we get? So, the little k, which is again the order of big K, but that's also what? The order of g to the d, but what's g to the d? Right. But there's we need to use the theorem from before. See here I have that it's n over d. Why is that? Daniel, stop that. Right. Oh, okay. So this means n equals 2. Yeah, dz. But apparently, but why does that? Why does z have to be k then? Is my question. And k is the order of the subgroup we're looking at, right? How about this? GD to the k, what's that equal to? And why is it equal to that? GD is what? It's a generator of this group, right? We know that the order of the group is k by assumption, right? The order of the subgroup is k, and we have a theorem from earlier in the section that any element to the order of the group is what? Is 1. But we have another theorem that says that if this is the case, it must be that dk is what? It's a multiple of n, right?
Yeah. So then you have n equals dk, k equals n over d.
Right.
So then g to the k is same as g to the n over d.
Right. Now, once we have that, why is this unique? Why is the subgroup unique? I mean, we're saying that this D is what? N over K, right? Where K is the order of the subgroup we're looking at, and N is the given order of the big group in which K is fitting. Well, that's a formula, right? I mean, we a lot of times prove uniqueness by we pick two arbitrary things and we show that they're equal, right? There's another way we can show uniqueness. If you have a formula that without ambiguity produces the object, that proves uniqueness, right? It's not as exciting as picking two things and showing they're equal, but it is in fact a proof of uniqueness. So g to the n over k is a specific thing that proves uniqueness. All right, let me try to redeem what's left of this discussion with an example. This might be better. Example 14. What are you doing? If you're not here, I'm sorry about the video. Let's see here. Z20. So look at Z20. So we looked at this a little bit ago, right? Additive, of course. And we can look at the subgroup generated by 4, right? Which would be multiples of 4. 0, 4, 8, 12, 16, and that's it, right? So does that make sense? I mean, sometimes another notation for this would be 4 times Z20, by the way. Sometimes that's a nice notation, right? So let's say, what I'm going to say is well, I guess I'll say G1. I'm going to use an H. I'm sorry. I forget my notes. You guys aren't looking at my notes anyway. H1 is the subgroup generated by 4, right? What's the order of 4? 5. Very good. Okay. So the greatest common divisor of k and 5 is what? Well, it's 1. That's what I want at. It's going to be 1 if k is equal to what? I mean, what are the numbers relatively prime to 5 is what I'm asking in a rather circuitous way. Well, this is kind of hard to mess up, right? 1, 2, 3, 4, right? Great. What does that mean? That means that by the earlier theorem in this section, 4 times 2, 4 times 3, and indeed 4 times 4 all generate H1. See, this is an illustration. We had a theorem that if you have a generator for a group, then if you take that generator and raise it to a power which is relatively prime to the order of the group, right, then that gives you another generator. Now in this context, raising to a power means you take a relatively prime multiple, right? And those still give you generators. Now this is not especially interesting because like everything's a generator except for 0, right? So only the 0 multiple lets us down. What's more interesting is if we add to this example H2, which is going to be 0, 5, 10, and 15, aka the subgroup generated by 5, aka 5Z20, just to throw that notation out there for you. So what's the order of 5? Right, the order of 5 is 4. Very good. And so if we want relatively prime k to 4, what is it? One or three, right? So that means only 1 times the generator or 3 times the generator will again be a generator for this subgroup.
Does k have to be less than the orders?
Well, I mean, you could make k 11, but that wouldn't change anything. Yeah. I mean, technically, if this makes you happy. I don't know. That's too far. Well, we could do that. I have defined it. I've begged the question whether or not that's well defined. We'll get around to figuring out whether or not it's well defined sometime. So this implies that 5 and 3 times 5 generate G2. All right? And indeed, that's the case, right? 10 is not a generator of G2 because what does 10 generate? It's an order 2 subgroup. It's just 0 and 10, right? So I see you there. I look back, he's like this. So, we stated this theorem about finding generators, right? What was the theorem? It was this. If G is equal to G and the greatest common divisor of the order of G and K is equal to 1, then G to the K is also equal to G. I mean, that's the theorem restated in a nutshell. So if you have an element, if you have a number which is relatively prime to the order of the group, which in this case is the order of the element, cyclic group. And of course, this, the G is cyclic, right? So then another way to generate this cyclic group is to take a relatively prime power of the generator. But don't forget, this applies to groups, right? So subgroups of a group are still groups, and this theorem still applies to each and every subgroup. So if you want to start with Z20, you can ask about how to generate subgroups by applying this to subgroups, right? Which I think is a point which doesn't always get made in textbooks. Ha! That almost bounced back. How many markers do you have? I feel like he took a whole box of them from home or something. Woo. Wait a minute, these are from my desk, aren't they? These are my markers. What? I don't know if this is really going to help you. Sorry, I think this may not be entirely. At least he's not throwing pens at me. Pencils. So that's what I say. All right. I think. What? No. What was that? Some sort of ninja tool? I mean, what is this? All right. Lecture 9. Finally. Sorry, in my heart, I know that every single proof in the cyclic subgroup section is actually relatively trivial. I just have a way of getting up here and making it complicated, and I apologize for that. I think that's all me, because I don't think these things are that complicated. It's really just remembering what you already know and going for it. So lecture 9, which now officially starts, is on homomorphism and isomorphism. And these are definitely, especially isomorphism, really, really important idea in here. And I've already told you before what this means. So we say, let me just give you a definition formally. Let's say if G comma star and H comma, I don't know, dot are groups, and let's say phi going from G to H is a function with phi of x star y being equal to phi of x dot phi of y for all x and y in G, then phi is a homomorphism. And if there exists a homomorphism of one group to another, then we say that these groups are homomorphic. So we say G and H are homomorphic, and write G is squiggle squiggle H. Okay?
Just be by check.
No. Homomorphic. Homomorphic.
Oh, okay.
if a homomorphism is also a bijection, all right? If a homomorphism is also a bijection, then we say phi is an isomorphism. Right. And then we also say that G and H are isomorphic. All right. And G and H isomorphic, we can express that by just writing the symbol G. So let's say equals with a squiggle on top is H. It's going to be isomorphic. Okay. Now last year I made the mistake of using the double squiggle for isomorphism, and I didn't have a symbol for homomorphism, and it was too late for me to notice it before it happened. Not bad. All right. So, we'd like to understand what are properties of homomorphisms, what are examples of homomorphisms, right? How do we construct an isomorphism? How do we use it? How do we find it, right? These are all questions we want to answer and ask. Other around, ask and answer. So let's see, start out small. So if we have, what's the only subgroup of order 2? What's it look like? We got what? A, B, B. So let's assume, we might as well say A is 1, right? So what has to go here? So you guys have thought about this some and you realize that, right? So this is just, if we have G, any subgroup, any group of order 2, it has to look like this, 1 comma B with this Cayley table, right? So what's this isomorphic to? Right, this is isomorphic to Z2. What else is it isomorphic to? What's that? I and negative I?
Just 1 and negative 1.
Oh, sure. It's also isomorphic to the multiplicative subgroup of Z. The group of units is Z, right? Yeah, -1 and 1, this guy, multiplicatively. Anything else? What's that? U2?
Square root of unity.
Yes, this would actually be U2. These guys are one and the same. That is, in fact, U2, because the roots of unity plus or minus 1. That's the groups. That's the second roots of unity.
Is any C2?
Any what?
Any C2?
Any C2? Sure, I'll take that. I would say that in some sense that's kind of exact. I don't know, but yeah, C2 is a good thing. How about this? The subgroup generated by a permutation. Pick your favorite permutation. For example, 1, 2. Sorry, I got to be careful here. These are not equal as point sets, except for here. So these are all groups of order 2, which are really the same group, right? How do you construct an isomorphism between these? What you can do is you just need to send the generator to the generator and then extend from that. That will actually define an isomorphism. That's a theorem that we should get to eventually. So let me go on here. Just to give an explicit isomorphism, how about this? Psi of 1 is equal to 1 comma 2. 1, 2. This would be an isomorphism from Z2 to the cyclic subgroup generated by the transposition 1, 2, which is, of course, a subset of Sn, right?
What if it's not a cyclic group? So you don't have a generator.
What's that?
What if it's not a cyclic group? You don't have a generator.
If it's in order 2, it has to be.
Well, if it's okay for order 2.
Okay.
Not order 2.
Well, you might have more than one generator, right? One of the theorems that we find in the isomorphism section is that if your group is finitely generated, in the sense that you can pick a subset of elements, that all other elements are obtained as products and powers of those elements, then if you map those I'm not saying it. I need to write it down carefully, but there is an extension to things generated by more than one thing, sensibly. Let's see here. Another example. This isn't really, so this was kind of a meta example, but I think it's a decent one. Example 2, what's the only subgroup of order 3? Right? This is for free. But if you think about it, let's see here. This has to be a squared, right? But for this to be a group, what does that have to be? If it's 1, then I think we get into trouble. Why can't that be 1? That can't be 1. That has to be B for reasons I'm not. Anyway, this has to be B for some reason. What is that reason? I don't know if we can see it yet, but let's see here. Oh, okay, so if thank you. If AA is equal to, what did we say? 1? If AA is equal to B, then what?
AB has to be equal to 1.
A, B. So you're saying if that, then that? Was your point?
Why is that not allowed, though? What if, like, can A and B not be inverses for each other?
Well, suppose, I mean, we're trying to think about what is a possible group of order 3, right? So suppose it's got three elements in it, 1A and B, right? So suppose that G is equal to 1A and B, where the order of G is 3. I want to just talk, and this was actually in an earlier section, right? But the question is, what's the possible Cayley table, right? This is argued explicitly in like 2.2. He gives the arguments there. But essentially through case-wise thinking, you can see that this has to essentially be what I'm about to write, but I'm trying to talk through it with you guys, if you guys can help me. You've studied that section, you know the arguments, I think.
AB and BA would both be 1 then. Because otherwise A squared and B squared are both 1. And then B squared would be A. Yeah, exactly. That would
So why does A times A have to be B again?
So in terms of the Cayley table, if A times A was 1,
Yeah.
then the remaining spot in that row would have to be B.
If this was,
That would be the 2.
then that would force B here, which is not, okay, very perfect, thank you. So that has to be B, right? And once that happens, this has to be 1,
Yep.
and this has to be 1, and that forces this to be A. Because we can't have repeats in a column or row. So, yeah, basically once it's kind of like reverse tic-tac-toe. Well, maybe it's actually exactly like tic-tac-toe. Once you get the middle spot, you win everything, right? I mean, like, so, you know, I took him bowling, and we played pool, and this is the thanks I get. See here. So, anyway, if you look at 0, 1, 2, 0, 1, 2, right? Z3, that's 0, 1. This one I'll do faster. Math. Right? You can pretty easily see that this is the same shape, right? You got this B like that, right? You've got 1, 1, 1, AAA, and the zeros are appearing in the same spots as the ones, right? So it should be evident that my G is isomorphic to Z3. They have the same shape Cayley table. Now the isomorphism we can define by just saying psi of A is equal to 1, and then extend via the group operation. Now, what do I mean by that? So I'm saying that phi of a to the n should be defined to be what? N times 1, right? And that will define the isomorphism. Because, in fact, of course, we know that b is actually equal to a squared. So, in fact, this g was nothing more than a sneaky notation or an alternate notation for the it was really just C3 in disguise, right? But okay, I'm sorry. Enough about this Cayley table stuff. Let's get on to the big boy stuff. Big boy, big girl theorems. Let's stop with this nonsense. I mean, it's great, but it's not really what abstract algebra is about. Abstract algebra is much more about what I'm about to do. So,
Just to clarify, it's the same that all groups of order 3
yep, there is only there's only one group of order 3, and it is Z3 up to isomorphism. Up to isomorphism. What does this term mean? It means if you take two different groups of order 3, they're in some sense the same group, but I mean, they don't have to be the same point set, obviously, right? But it's really just a change of notation. The group structure is the same. This is, of course, very much, oh man, in my eyes. This is the same terminology as we use in linear algebra, right? Where we learned that if we have two different 10-dimensional vector spaces, then in as much as the linear structure is concerned, those are kind of the same thing, right? All right.
How long does it get before that breaks down? Like, is a group of 4, you have more than one of those? Like, what is the turning point there?
Yeah, so of order, example 3, we have C4 and we have K4. And those are the two cases. This is actually basically proved in the earlier section. Yeah. So you either have something that has the form, A with a to the 4th equal to 1, or you have something that's generated from A and B. I mean, it's actually 1, A, B, and AB. And these all have order 2, the Klein 4 group as it's called. The Klein 4 group can come in disguise, though. See, this is isomorphic to Z8 group of units. And I can tell that immediately because Z8 group of units has 3 elements of order 2, right? Now I'm starting to use things that I haven't yet developed. So let me prove a theorem. Here it is. If we have phi going from G1 to G2, right, a homomorphism, then phi of E1 is Daniel, stop. Enough. Thank you. So the identity maps to the identity under a homomorphism. And 2, if we have phi of G inverse, guess what it is equal to? Phi of G inverse for all G. And let's see here. Let's see, what else can I tell you? Curses. There's a result on, there it is. Furthermore, 3, phi of G to the n is equal to phi of G to the n for all G and G1 and n in the integers. This is not surprising from what we know about linear algebra. Remember? I mean, what is a homomorphism? It's essentially a linear transformation, right? With less structure, but it's the same idea. So think about a linear transformation where you only talk about addition. That's what a homomorphism is, because any vector space is a commutative group with respect to vector addition, right? It's got 0, it's closed under negation, it's associative, right? And of course, it's commutative as well. So every linear transformation, right, from linear algebra, is a homomorphism with respect to the additive group structure of the vector space. And that's the reason 0 maps to 0, and we can pull minuses out. Because that's what this basically says, is you can pull a minus out. Right? And this down here says that this is like repeated additivity. You know, linear transformation of blah plus blah plus blah plus da-da-da plus blah is, in fact, you know, the image of blah plus the image of blah plus the image of blah plus, you know, it's essentially that. Anyway, let's prove it. So how are we going to prove 1 there? How about this? E1 times E1 is equal to what? E1, right? It's hard to go wrong there. So phi of E1 is equal to phi of E1, which means that phi of E1 is equal to phi of E1, right? Which by cancellation in G2 implies that phi of E1 is equal to E2 by cancellation in G2, where I'm using E2 to denote the identity in G2. There you have it. Yes, Daniel? How much longer? This is thought by students, but it is not to be spoken aloud. That's what yeah, you got to listen to him. He's the president. So, the president says goes. Yeah.
2 minutes.
Oh, you think you said 45 minutes? Why didn't I 45 minutes?
I didn't say 45, I said not president.
Or you said 4 to, oh, I heard I thought you were, you missed the,
I said 2 minutes.
he threw his voice over to your direction. I was confused. I got 5 minutes. All right. I'm going to make it 10, though, on the basis of interference. Flag in the play. All right, anyway. So 1 is shown. 2. I think you can guess where the proof is going to go. GG inverse is equal to E1, right? So phi of GG inverse, that's just fun to say. Phi of GG inverse is phi of E1, which is E2 by 1, right? But by the homomorphism property, that's phi of G inverse equal to E2, right? And likewise, we also obtain, in the same fashion, we find that phi of G inverse phi of G is equal to E2, right? I can do the same argument starting with G inverse G, right? So I get that this phi of G inverse is what? It's both a left and a right inverse to phi of G, which suffices to prove by the definition, of course, that phi of G inverse is equal to phi of G inverse, G being arbitrary. There you go. This is so restful. Like, cyclic groups are such a drag. This is fun. I can do this. Hey, you monster. You monster. All right, let's see here. 3. See, he was a bad influence when I brought him to linear a couple years ago. He wrote math is boring on the whiteboard. I see he hasn't changed. Let's see here, can't be trusted. Suppose that phi of G to the n is equal to phi of G to the n for some n in n, right? By the way, is it true for n equals 1?
Oh, we're done.
40, this is not a... That's not how it works. There's still, stop this. And you stop being so happy that he's doing this. Because you're just as bad. This is clearly true for n equals to 1. And so by induction, let's look at phi of g n plus 1, which would be phi of g to the n times g by definition of exponents, right? Or laws of exponents, whatever you like. So that's phi of g to the n times phi of g. But by the induction hypothesis, this is phi of g to the n, phi of g. My phis are degrading, sorry about that. And then again by laws of exponents, or the definition, depending on how you started your discussion of exponents. There you go. So that proves by induction that this identity is true for positive n.
I just can't do that in a minute.
Very gracious.
What about negative n, right? Because I don't want this just for, I want this for all n in the integers. So how do we get negative n?
Combine it with the result from 2.
Right, so I think that's pretty much it. If we combine with 2, then we extend to negative n, right? So then use 2 to extend to z.
In the case where n0 is just part 1.
Right, n equals 0 is also just clear, right? But it's 1 also, thank you, yeah. So, sorry I didn't get more done today. You'll forgive me. Thank you for your homework. Have a good weekend. Yeah, you can stop it. You can hit stop. Help him hit stop if he hasn't already.